In this video, I'll solve a single-stage distillation practice problem. It says a mixture that is 30% benzene and the rest toluene, and benzene and toluene form an ideal mixture, is fed to a single-stage distillation process that operates at 1 atmosphere at 100 C. The feed is a subcooled liquid at 25 C and 1 atmospheres and flows at 200 moles per minute. Part A asks to predict the molar flow rates and compositions of the product streams. Really quickly, before I begin, I want to discuss the nomenclature of subcooled. Subcooled just means below the bubble point. So for all intents and purposes, a subcooled liquid is just a regular liquid that is not at the bubble point. So I'm just going to write that. All right, so the first step to solving any chemical engineering problem is to draw a process flow diagram. So I want you to pause the video now and see if you can draw a process flow diagram, incorporating all of the necessary information from the problem statement into your diagram. Okay, here's my diagram. I've got a feed of 200 moles per minute coming in at 30% benzene. I've also designated benzene as my component A because I happen to know that benzene is more volatile than toluene. But suppose you didn't know that, you could figure out which one is more volatile by looking up what the boiling point of benzene and toluene are, and then choosing the one with the lower boiling point. So I've got the feed information. As I said before, the feed flow rate and the composition are more than likely always going to be specified for a separations problem. My unknowns for this part A are going to be the V and L flow rates and the YA and XA compositions. And because I've specified what the temperature and the pressure are for the distillation stage, I've specified my 2 intensive variables that I need for Gibbs phase rule. And therefore, I've got 4 unknowns left and 4 equations to solve them, which are going to be the 2 material balances and the 2 phase equilibrium relationships. One more parenthetical note before I start deriving the equations and solving them, that if we wanted to know what the temperature and pressure were of the outlet streams, we typically say that whatever comes out of the stage is at the same temperature and pressure, unless there's something else that's changed about it, but that'll typically be changed after it immediately comes out. So I mentioned before, I think in the summary notes for this video, that just practically speaking, you never want to pump a vapor around, or you could pump a vapor around, but it's just that liquids are a lot easier to handle than vapors because they take up way less space and you don't have to contain them. It's like if I wanted to pump a vapor into an open storage tank or something, I couldn't do that because the vapor would float away and I'd lose it. So typically what you'd do afterwards is in post-processing, you would pump this to some kind of condenser, and the total condenser would condense all of it into a liquid product. But that's kind of just parenthetical practical note of how this usually goes in industry. But just for the purposes of solving the problem, we won't worry about that too much for now. Just to say that the outlet streams have the same process conditions as my single stage distillation unit. All right, so the next step, now that I have my process flow diagram written, is to predict the molar flow rates and compositions. So write out your 4 equations and start to solve them. So here are my system of 4 equations. The next thing to do is to analyze this system of 4 equations to determine which equations are going to be easiest to start. So what I like to do is circle or underline my unknowns, and I'm looking for any equations that have only one unknown. And if not, that's not going to be the case here. Where can I start solving? So also notice that I haven't figured out what PA star is yet. That's something that I'll have to calculate. So P star, I have to take a quick break and find with Antoine's equation. So remember, component A is for benzene. So I need to look up the Antoine's constant. So you could do this. Your textbook, Lane, has some Antoine's constants in the back, or also the Felder, Rousseau, and Bullard textbook from MEB has these in the back, or the NIST website. So PA star for benzene, or the equation is 10 to the power of A minus B over T plus C, where you look up A, B, and C in any of the sources that I just mentioned. The vapor pressure of component A at 100 C is equal to 1350 millimeters of mercury, and the vapor pressure of toluene at the same temperature, 100 degrees C, is 556. So once again, this is also how you know that benzene is more volatile, because the vapor pressure is higher. So once I have these known, I don't have to circle them as unknowns anymore. All right, so from a problem solving perspective, I've got the first equation has V and L as unknowns. So 2 unknowns there, I can't solve for that. The component A material balance has 4 unknowns, so that's probably going to be the last one that I solve for. And the 2 Routs laws just have YA and XA as their unknowns. So this is going to be a system of 2 equations, 2 unknowns that I can solve for right off the bat. And looking at this, the easiest thing to do would probably be to add them in order to eliminate YA. So if I start the problem by add Routs laws, I've got YA times 1 atmosphere plus 1 minus YA times 1 atmosphere. That is all going to cancel into 1. So this 1 atmosphere can be factored out. YA plus 1 minus YA is just 1. So I've got 1 atmosphere on the right. On the left, I'm sorry. Keeping sure to keep my units constant, right? Because I have vapor pressures in millimeters of mercury, I have to have dimensional consistency here. So instead of 1 atmosphere, I'm going to write equivalently 760 mmHg is equal to XA times 1350 mmHg plus 1 minus XA times 556 mmHg. All right, so now I've got 1 equation, 1 unknown, which I can solve for XA. Solving this 1 equation, 1 unknown, gives me that XA is equal to 0.257. Just to quickly check, remember my ZA was 0.30. Component A is going to be more volatile, meaning it's going to be enriched in the vapor product and depleted in the liquid product. And here I have a liquid composition that is less than what I started with, so everything is making sense to start off. Now that I have XA solved for, I can then plug back into either one of the Routs laws in order to find YA. So plug back into Routs law A, it just looks a little bit easier. Plug into Routs law for A, and I will get YA is equal to 0.257 times PA star, which was 1350 mmHg, and divided by 1 atmosphere, or 760 mmHg. And computing that value gets me 0.456. So once again, I should have a vapor phase composition that is greater than my feed, and that is true. 45.6% is indeed greater than 30%. Now that I have YA and XA solved for, I can now solve the combined system of the overall material balance and the component A material balance. So in order to do that, I guess the easiest way would be to probably substitute these variables in for each other. So I can solve for V in the overall equation by saying it's 200 minus L, and then plug that into the component A balance. So just performing a little bit of algebra can get me to solve for L. So this is my, again, component A material balance with all the things that I know plugged into it. So I'm just going to calculate what L is. My answer here is 157 moles per hour for L, and now I can go back and plug that in for V, which is 200 minus L. And solving for V then gets me 43 moles per hour. All right, so notice a couple of things. I'm truncating all my answers after 3 significant digits. I'm kind of picky about, I'm not very picky about significant figures, but I do get upset when I see too many significant figures. So please never give me an answer that's more than 4 significant figures. That's set as the cutoff for this class. So 3 is more than sufficient in a majority of cases. I would say 3 is sometimes even overkill. 2 is sometimes probably the best for most problems. Because once I get too many significant figures, then the numbers start to lose their meaning. All right, so I've solved this problem, and I'm just going to go up and plug in all the numbers that I had in my process flow diagram such that we can talk about it a little bit. Okay, so I've plugged in all the information, and I wanted to note that say our goal was to obtain pure benzene, right? We only got to 45.6% benzene. We have not come close to having a pure, I would call a pure stream like above 90%. So a lot of times when you're doing single stage distillation, you're going to find that you cannot get nearly pure products. You're going to be limited by what phase equilibrium says is possible. And the second point I wanted to make was there were 60 moles of benzene coming into this process, right? So 200 times 0.3 is 60 moles of benzene, and then 140 moles of toluene. How much of that benzene can we get back out of the process? So the TOPS product, or the vapor product, is going to be our benzene-rich stream. We only have 43 moles of that benzene recovered at 45.6%. So the point I'm making is that single-stage distillation is not very effective for performing separations. And in order to increase the efficiency of your separations, a lot of times this is going to require multiple stages, and that'll be kind of what we talk about next. But before we talk about that in more detail in a couple of class periods, let's go into part B. If you wanted to obtain 95% pure benzene in the vapor stream, could you do it in this single unit given the same feed stream? What temperature would this require? So the process flow diagram is going to look very similar, except we're now going to change what the unknown and the known variables are. So try to draw that process flow diagram. So here's my process flow diagram for part B. Again, the only difference is that I now have temperature as an unknown variable, and I've set the specification that my product has to be 95% pure benzene. So as the engineer, this is typically how you would solve a problem like this, is you'd have a feed mixture that you want to separate, and you'd have some type of goal or target that you're going for. So I've specified I want 95% pure benzene. What temperature do I have to run in order to make this possible, in order to complete the problem? So let's go ahead and write our 4 equations again. Same 4 equations, we've just changed what the unknown variables are. All right, so same 4 equations, again, just mixing up what is known and unknown. I'm going to go through and circle my unknowns. V and L, V, XA and L, XA, P and T, XA and T. So once again, if I combine my 2 Raoult's laws and solve them, I've got 2 equations, 2 unknowns. So just if I combine these, again, my 760 is going to factor out, and I'm going to be left with just 760, since YA plus 1 minus YA is equal to 1. 760 mmHg is equal to XA times PA star of T plus 1 minus XA times PB star of T. And at this point, I recognize I'm running into a wall with my problem-solving procedure. And actually, there's multiple problems here. So first of all, by adding the 2 Raoult's laws, I can't use this as a solution procedure because I failed to eliminate one of the variables. Remember last time above when I was doing this and I added the 2 Raoult's laws together, my YA dropped out of the equation such that I only had 1 equation for 1 unknown. But now that I'm trying to add the Raoult's laws together here, I don't have that happening. I still have XA and T as unknown, as 2 unknowns in this 1 equation. So I can't use this procedure to solve. The other problem that I have is that when I had temperature solved for, I could simply plug in what the vapor pressure was. Unfortunately, I can't do that here. So if I wanted to solve this analytically, I'd have to eliminate PA star, and I'd have to say this is 10 to the power of A minus B over T plus C, where A, B, and C are all parameters for benzene. I have to do the same thing for PB. So 10 to the power A minus B over T plus C. Now, the only thing that you can do at this point is there's still 2 equations, 2 unknowns, so you could solve for them, but you can't do this algebraically because it's nonlinear. So this is where using Excel and using goal-seek and solver can really be helpful here. So I'm not going to show you the mechanics of how you'd go through and solve this just yet. I want to focus on just talking about the problem before I talk about or showing you exactly how you would use solver. So I'm going to go ahead and solve that now, and I'll just tell you what the result is when you solve for XA and T in the system of 2 equations, 2 unknowns. So the result of just solving these 2 equations, 2 unknowns, is that XA is equal to 0.88 and my temperature is 82.6 degrees Celsius. So if you plug this in, I'll tell you what the vapor pressures are as well. So PA, which P of benzene, vapor pressure of benzene for 82.6 C is equal to 819.9 mmHg is what I got. And PB star of 82.6 0.6 degrees C is equal to 318.2 mmHg. So again, if you plug this in, you should get agreement in these two equations, which mean it's a mathematically valid solution. However, the issue comes when you try and solve the problem further. So we've got the composition of the liquid stream, but already you may be noticing that something is odd. And that is if my vapor stream is 95% and my liquid stream is 88%, both of these numbers are greater than what we started with. So how is it possible that the more volatile component can become enriched in both streams? And if we go further and we solve for V and L in this problem, we'll find what the issue is. When you solve this system with two equations, two unknowns, you get that L is equal to 1857 moles per hour, and V is negative 1657 moles per hour. Now, obviously, you cannot have a negative flow rate because that means that the flow should be going the opposite way. So what happened here? In this case, we've broken and violated the material balance. So we cannot obtain in a single stage distillation unit a vapor that is 95% pure, starting with a feed that is 30% pure. So this is what I mean by the system has to obey the material balances and phase equilibrium relationships. So the answer to the second question is no, you cannot obtain 95% pure benzene in a single unit, given this feed stream, of course. If your feed stream was something different, then maybe your material balances would work out. So next time I'm going to talk about a way that we can solve this problem with a graphical approach, and it'll hopefully be a little bit less strenuous, because while it wasn't too much trouble to write these equations out and solve them algebraically, we're going to find that a lot of times in separations, a lot of the equations are going to be repetitive. And solving them graphically can give us a faster and easier way to get our answers faster, so that we didn't do all this work and then find out in the end that this separation that we were trying to make happen isn't actually theoretically possible. So after that, we're going to talk about some of the trade-offs that you can get. So I mentioned in the last video that the more pure product that you want, the less you'll make. And we saw that in this example because we had a highly pure product, right? We had 95% pure vapor. And I said that that usually correlates with the less product that you'll get. And in this case, we had such a pure specification that the flow rate that we specified was actually negative. So if this isn't possible, then what is the theoretical maximum that we can get if we sacrifice on our yield as much as possible? These are all things that we'll talk about in the coming class periods. That's all for today. Thanks for watching.